My name is Mike Powell. I'm Director of Lands for the Nature Conservancy in West Virginia. I appreciate everyone showing up this morning, taking time out of your day and your life to come and join us and learn a little bit more about Ice Mountain and what we have going on here, and most importantly, volunteering your time to help going forward, sharing the responsibility with Steve and all the other docents that we've worked with over the years to take people up and down the mountain safely, give them information about what they're looking at, introduce them to the area, and talk about the Nature Conservancy and some of the work that we do. So it's not real complicated. You can make it as complicated as you want. We have Dr. Steve Kite here that can really make it complicated. But the good thing is that Dr. Kite can take a really complicated concept and distill it down, and that's what we're really thinking about.
Or make it more complicated.
Or make it more complicated. And when I think about leading walks and taking people out into natural areas, the thing that I think about is distilling it down. Basically, you're wanting to talk to people on about a 5th grade science level, so you don't have to make it real complicated. You'll identify quickly those people that want to know a lot more, and depending on how much you've learned and how much you understand it as well, you know, you may go deeper. But the idea here is that we're taking people up the mountain safely, getting them back to their vehicles, showing them a good time, representing the Nature Conservancy, talking about Ice Mountain and all the wondrous things here, and that's the extent of what we're asking you to really learn how to do. So I'll let Steve talk a little bit about some of the geology. The idea is that we're going to go to the top of the mountain first, which is opposite of how you'll usually do it. And the reason we want to do that is because as it gets a little bit warmer today, the cold air coming out of those vents is going to be more dramatic. So if there's anyone that doesn't want to go to the top of the mountain, just catch me to the side and we'll talk about how to meet up so that we can take everybody down to the ice vents in the second part of the afternoon or of the morning trip.
Are you ready to talk? I am not going to do a geology lecture now, but I do want to make a handout available to you. Unfortunately, we have much better response than we thought. I have a few I can make up in addition to the ones I have here. But this is like, you see on the walls here, there's a couple of different posters. 2 there and the 2 there, they make up presentations that myself or my students have made at professional meetings. There's a lot in there, and I've tried to simplify it, bring it down to back-to-back pages, okay, on one sheet, and I put it in a little holder here so that if you think you're going to be leading trips and you want to have some resource to go back on to talk to people about the geology, which is on one side, how the plumbing system works in the ice mountain, that's on that same side, and then our temperature records on the other side. I have these available for you. Again, I didn't make up quite enough because we had more people I thought, but I'll just go ahead and pass this around. And what I'm recommending, some of you might want to take it with you. Some of you might want to now put it in your car so that you have it if you're leading a trip and want a geology resource. All right? Or some of you might just not want to have it because I do geology all the time, and I remember went to the desert Southwest on a sabbatical in Arizona once. And my daughter, who was 13 at the time, after we had stopped at the umpteenth national park, and I started explaining the landscape, she said, "Shut up, Dad!" But 13-year-olds do that, you know. I don't want to hear why anymore. I just want to be able to stop and say it's pretty. So I have this problem that, you know, think of the most beautiful landscape, natural landscape that you've ever seen. I'll be there analyzing it. So I know some of you just don't want to do that. It's, you know, a different kind of exposure. But these are, you're welcome to have those. Again, I have them with me. I just haven't made them up with the plastic folders if we run. All right. Again, yeah, I'll try not to overdo the geology. It's not incredibly complicated, but there's a lot of nuances, and it's working on different time frames. The rock is really, really old. All right, the rock around here is roughly, I should have looked it up, 360 million years old. When the landforms that we're going to be looking at evolved, the rock around here was 360 million years old. All right, you know, we go back to the Pleistocene, the Ice Age, and start talking about these things. What you got to remember is that in the timeline that is all of the Earth's history is stretched out on Mountaineer Field from end zone to end zone. That all of human existence is the width of a hair. Alrighty? And the age of these landforms around here is like 3 hairs. So, you know, it's just so recent on the big time frame. So there's going to be kind of this shifting of time, you know, between Ice Age and Rockwell. The rocks were already here and were really old already. But anyway, it's a complicated story I don't want to get too far into now because we need to get out and get some energy.
Yeah.
Hey, very quick question. Does this phenomenon exist anywhere else in the continental United States? I've never heard of another ice mountain anywhere.
There are about 200 of them in Iowa and Minnesota.
Okay, so it is actually pretty.
Yeah, the term I think is up here in one place. Yeah, up there, algific talus slope.
Got it.
I will take it because I'll probably, since you've raised this, and I bring it there. There are also, I think, dozens in the Appalachians. Although this is one of the colder ones. I got one colder one at Little Beartown State Park, but it's much higher elevation. So I think the temperature contrast is more rugged here. There's a number in Pennsylvania, and there was actually a publication in 1900 by Edmund Balch that inventories about 15 of them in Pennsylvania, New York, New Jersey. Yes, he did recognize this one. In fact, but yeah, they're here. But this one is exceptionally the biodiversity associated with it is not. Well, it is unique in the exact assemblage that you have here. I don't think you'll find anyplace else. But it is one of the more exceptional ones in how many northern plants you have. There is one though in Pennsylvania, where a buddy of mine was studying, and they turned up with a new species of lichen that had never been described before from that site. So, yeah, they're special. This is one of the best of a really neat, unique landform.
So one of the really cool designations for Ice Mountain is a few years ago we were designated a National Natural Landmark. There's 300, I think, of those, 300 plus of those all across the country. The program's administered by the National Park Service, so it doesn't really change how we operate or manage the mountain at all. It's just a national recognition of it being a special place. And the way they nominate these places for review for National Natural Landmark status is they compare them to similar areas. So this specific one was compared to other cold air producing talus slopes like the one in Pennsylvania that Dr. Kite mentioned and several others throughout the eastern U.S. And this one became the nominee for a few different reasons. One is that collection of biodiversity that Steve mentioned. So biodiversity meaning different types of organisms. The most unique biodiversity here is probably the plants. Many of the plants that you'll see here at Ice Mountain typically grow above 4,000 feet in West Virginia and this far in the southern U.S. Most all of them are found much further north in Canada and even around the Arctic Circle. So the biodiversity was one thing. The fact that it was protected land by the Nature Conservancy was another factor. We have a long-standing history of managing land responsibly. We have a long history of being an organization that exists over time, meaning some of these nonprofits will exist for a little while and then they don't exist anymore. They don't have the funding or whatever to keep going. So the fact that we have a long-lasting track record, and then the biggest thing, honestly, and I talked to both the reviewers and the folks at the National Park Service who actually approved it, was the fact that we had trained docents that took people up onto the mountain to teach them about the uniqueness of the area, how to enjoy the area responsibly, and the fact that we allowed visitation in a way that people could come, but they weren't just turned loose. And so the fact that we could keep an eye on things, regulate it, keep permanent protection on the site, and keep people away from the places that are fragile and unique that we're trying to protect. So really it's you all that help push Ice Mountain over the hump to become National Natural Landmark status.
I can add just one little other item. There are thousands of talus slopes in the Appalachians. Less than 1% of them are really ecologically ecosystem changers. I mean, they're often a little bit colder. If this temperatures, the temperatures I see in the vents, would be temperatures you'd have if we had a mountain 7,000 feet tall here. So it's
At 900
yeah,
feet,
it's,
a little over 900
745 for the bits.
for the low vents.
Yeah,
Nice.
yeah. So
I was wondering, of course, there's a lot of impact right there at the ice regions. What is the sphere of influence? What is the area in which there is a significant impact that's influencing the ecology with this colder air?
do you want to get?
I mean that's the geology of the mountain, really. Why don't we? Let's put a timeout on that,
Yeah,
because
yeah,
I think
yeah.
that you'll be able to visually see that area in a little bit. And there's a couple spots along the trail where you can almost see that entire sphere of influence.
Yeah, the cold air vents are in a belt no more than 60, 70 feet top, not vertical, but
Right.
from one side to the other side, and they run along a strip. So it is really local, and I think once upon a time there were probably many, many more of these that got destroyed when there was road building, railroad building, or whatever went on in the historic past. In fact, there's one in Pennsylvania that a geology friend of mine said he remembered it as a kid, and then they widened US 11 or US 15 or whatever it was, and went away.
Where's the one in Pennsylvania? Out of curiosity. The one in Pennsylvania, where's that one?
Spruce Creek?
Spruce Creek.
Yeah, is one, and I don't know the exact ownership of that. I think it is held as, oh, the Conservancy, the Pennsylvania,
Western
Pennsylvania Conservancy, I believe, is one that mines that. It's not as widely visited as I thought.
Steve, you mentioned this lichen that had been discovered in a similar place, and it seemed to be unique to that. I mean, it was a new type of lichen. I'd always thought of the plants here around where the ice caves are as being you could find them everywhere. I mean, you could find them other places, but not at this elevation. You could find them up in Canada or up in alpine meadows. But are there any plants in this here at Ice Mountain that are unique or really rare that you don't find very many places?
I'll give a response, and then Mike, you can add. But
Globally, no.
Okay.
Most all of the plants that are found here are relatively widespread where they occur,
Yes.
except for in the Appalachians, in the southern Appalachians.
Bristly rose is, like it's here, and maybe one or two other places in the state. It's not in Pennsylvania. It's not in Ohio. It's not in Illinois. Not in Indiana. It's not in Maryland. It's not in Virginia. Alrighty. But then once you get into it, up into Michigan, into New York,
Yeah.
it's the most widespread rose in the world.
Okay. Yeah.
But I think that part of the story with that lichen is not many people study lichen, so it may actually be elsewhere.
Oh, I see. Okay.
But
Okay.
also, though, it may be that it's been isolated long enough, like the cheat creature snail, whatever it's called now. It's just so isolated. It has been isolated long enough time. It's certainly been isolated 11,000 years.
Yeah, I didn't answer that precisely. So up north where these plants occur,
Right.
they're most of them are very common.
Okay. Okay.
But as you go further south and extend their range to the south,
Right.
they become much more rare and localized.
Great. Great. Thanks.
Real quick, so if you haven't signed up your name, phone number, email, let's go ahead and get that form going back around again. So basically the way these hikes get scheduled is people go to our website, or maybe they found Steve's specific site and navigate to that to do a request, and then Steve gets a request to him on the date that folks want to come, who they are, how many they are, things like that. And a lot of times Steve does the hikes himself, but what we're trying to do is get more and more people involved and ultimately get you to where you're leading hikes to the top of the mountain as well. So the way he keeps in touch with people is primarily through email. We did ask to put your phone number. We can keep coming a little bit. Yeah, there's benches here and there. If anybody doesn't want to go to the top, you can wait for us here. Nobody said they didn't want to go, so I'm presuming everybody's going to go to the top.
Yeah, that's what I wanted to talk about here, because in leading a trip, this is a point that you're going to be making a decision on whether or not you drag everybody up to the top of the mountain or not. Very often, if I have a short amount of time, there's really not a lot of time to go up there. So if I'm here with students, I only have 2.5, 3 hours. We go to the vents and come back, and that's it. But I almost always make a point of going up to the top and back. If everybody's fit, it adds a little over an hour to the walk. But again, this is just a point in time where you do a couple things is, explain what you're doing so people have an opt-out, and then also point out where they turn. If they, again, it's a good idea to always be the front person or have a front person that knows what's going on, but you want to point this sign out, Raven Rocks and Riscony Sandstone, we'll talk about that up on top, but you want to make sure that people who might have jumped ahead of you coming down will stop here and wait for you.
Where we've lost people is coming down off the ridge, the sign that says development.
Oh yeah, that one.
Yeah, that's an easy one.
Yeah?
Yeah, and
We've tried
ideally,
blocking that
everybody comes as a group and leaves as a group. But inevitably, you're going to have people that need to leave early, that physically feel they can't do it anymore, or whatever. So that's the time when you need to be really aware of where you are, and then think about those intersections returning so you can describe to people how to get back. Steve, when you're leading the hike, would you normally go the ice fence first? Yeah, and that's the way I would recommend it too. And then because it's a decent huff coming back up to this point from the ice fence. So at that point, most people will know if they want to go an additional 450 feet up. It's well worth it. I mean, the view up there is spectacular. And there's some cool stuff in my mind from a forest ecologist standpoint that is so drastically different over here than what we were seeing. But obviously, for most people, the keystone, the thing they want to see, are the ice vents. So that's why, for me, it's always good to take people there first.
But the reason we're doing it backward is because the temperature contrast will be greater later in the day. And so this is a great time of year to run this trip, especially if it warms up in the afternoon, because you might have some of the imagery I have, there's over a 50-degree temperature difference between the outside air and the air coming out of the vents. And that's what we're kind of waiting for it to warm up a few degrees to get maybe a 30-degree difference we might see today.
Yeah. Any comments, questions, real quick before we keep going again? Anybody? We're good?
Have I met you before? I don't think so. I came with Marge.
Following in the herd.
Let me just see how many people were paying attention. It's a quiz. It's a quiz. I'm a professor. I got to give a quiz. All right. How many of you saw over the last several hundred yards any rocks bigger than this?
No, they're all small shells.
They're all small shale pieces. So most of the rocks that you saw were like fingernail size or thereabouts. Because the geology, you will not see the bedrock. You did see a tree throw that brought some rock up. So this is a Devonian shale landscape that's underlain by. It's not what's on top of the mountain. Now in a little bit, we're going to walk into cobbles and boulders that are coming down the hillside. I wanted to draw your attention to it. One of the reasons I want to draw your attention to this, that somewhere in here, and it might be right there, we're going to cross the Marcellus Shale, okay? Which has absolutely no economic value.
Yeah, that's right. They can drill for gas.
It's baked too high for there to be gas in it, and it's too close to the surface. So this will never be a site of oil and gas exploration over here.
Knock on wood.
But it is an interesting link to what's happening at the surface here, and then all the oil and gas developments happening over in western Pennsylvania and north central West Virginia.
So if we feel an earthquake, don't worry about it.
We'd be lucky, but I wouldn't want to be right there.
Not under that tree.
Yeah, yeah. Those earthquakes are mostly waste disposal. The actual shale mining.
Steve, quick Steve story. I loved it. We were down after the 2008 storm, all this stuff hanging up in the trees and such, and a bunch of us are kind of tree huggers, and they're, oh my goodness, this fragile plant. How are we going to get these trees out of here? Long faces. Steve's coming in like a kid that, just been released to the playground. Oh, this is so cool. Everything's opened up. We can study what effect this has on, he's the scientific mind going going wild.
Disturbance is natural, right?
You know, hey, I am, the kind of geology I do is earth surface processes and landforms, glaciers, wind, river deposits mostly in this part of the world, gravity, you know, tree throws, that sort of thing. Around Morgantown, we had a lot of rain, and we've had tens upon tens of landslides. To which I respond, cool.
Hey, real quick, one other thing too, as far as like a trip leader kind of tidbit. So when you stop, it's always good to make sure there's not a humongous hazardous tree above where you're standing. So we probably chose, at least for like this third of the group, not the best place to stop. But, you know, also when you see features like this, keep your group moving by them. I mean, it's not likely this thing's going to fall while you're here, but it certainly could.
We don't have to stay during a windstorm.
They are fossil brachiopods from an old beach. This sandstone that we're walking on it's an old beach environment from 360 million years ago. There was deep water at the time over here, then the Marcellus Shale was deposited. On this side there was shallow water, on this side was limestone. But the ridge is held up by this hard sandstone. And somebody said it looks like quartz. Well, it's because it's made of quartz. So if you know geology 101 kind of level, then you know, you could probably look at this and make out the little sparkles, and so that's quartz.
You would call a guy a liar for 100 million years, would you?
It's hard. It's chemically resistant and it's physically resistant, so it holds up this ridge. Without the sandstone, there'd be no ice mountain. And that's what rock is going to be coming down on the other side to form the talus slope that we're going to spend more time on. So this is you know, part and parcel, this whole thing. I'll get a geology cross-section out of one of my handouts on top so we can talk about what the geology is up there. So
Steve, do you have the fluting on yours?
Fluting.
Is that what it's called? The there's a one that shows the
ridges.
The wormberg.
The ridges themselves.
Yeah, okay, that is one, and that's fossil. You got two of them, right? Yeah, three of them right there. This is great, Steve. Thank you.
That area.
You know, this is right.
Yeah, that's
Let me
right.
tell you what a brachiopod.
You are so
They're
busted.
around, they're really rare in the world's oceans today, but their lifestyle was like a clam. So they burrowed in the mud. They had little filter things that they got particles out of the water. It was actually totally different class, but nonetheless, they live like clams, although they're not clams at all.
Yeah, don't they have a projection?
Yeah, they have a stalk that projects attached to the ground.
Count.
And so their shell
Is this
would be
light
there
blinking?
moving around. They don't
Okay.
burrow the way that clams do. They don't have a foot. They have I think it's called peduncle or whatever attaches them. But they're still.
That's a botanical term.
Yeah. Anyway, but you're right. So this rock that Steve picked up right here is probably the best one that I've seen up here. So just something for you to point out to your group so that you can catch your breath as you're going up the hill.
Real quick, just another.
Just leave that rock there so that we have.
Yeah, absolutely. Yeah, you can put it up here on this old stuff. So what do you guys notice? Who knows their trees? Does anybody? What do people notice about the trees right here? Species.
They're budding.
They are budding. Yeah, they're starting to leaf out.
Covered in lichens.
Covered in lichens. A lot of pine needles. Okay, so what that mean? We have pines in the overstory. So right here, what we're looking at is mostly the short needle pines are Virginia pine. They have smaller cones. The longer needles are white pine. They have the bigger, longer cones. As we get up on the mountain, there will be pitch pine and table mountain pine. So, okay, so we have a lot of pine. What else? Oak, right. So we have a lot of oak. And another species that was relatively common on the way up, but we don't quite see it as much up here. Well, serviceberry certainly in the understory. I'm thinking of another of our overstory trees, hickory. So in general, this is kind of an oak, pine, hickory forest on this side. Drier, more sun, hotter, generally has an association with fire. Most ecologists would call this a dry oak heat. So we were talking on the way up, some of the understory shrubs that you're noticing are blueberry shrubs. So this is a plant community that is relatively static over time. It could have a relationship with fire, so it could set it back in a trajectory of what we call succession, and then it starts rebuilding again with a similar suite of species, because those species have dropped their seeds here. They have adapted their environment to be conducive to the plants that grow here. They have the geologic forces, the aspect, so they have all the ecological things they need. So a lot of times, you know, right now fire is a hot topic. A lot of fires happening in the West especially.
What a thing to say on a cool field trip.
But we're seeing a lot of fire issues come east as well. And I think one of the things as naturalists that you need to become comfortable with is fire is not bad. Fire in human landscapes, houses, buildings, is relatively bad. Fire in forests is not. So keep that in the back of your mind and maybe do some additional research to learn about fire ecology, fire-driven ecosystems, appropriate use of fire, appropriate places for fire to occur, and be able to answer those kinds of questions. Because a lot of people, when they come on these trips, they're ready to soak up information. And if we can better relay the message that not all fire is bad, the better we can do at putting fire intentionally back into the landscape, letting fires burn when they can and need to save lives and resources and to better serve the ecology of the site. So,
I was just wondering what type of oak you
yeah,
growing up here, because these are very different from.
Sure.
I
I'm
don't even know
not
if you
good
can
at
make them
looking
into
at the
a whistle.
acorn and telling you. I'm much more of a leaf kind of guy. So
Oh, they do make a good
oak leaves take longer than most leaves to decompose. So in an oak forest, you can almost always still find the leaves from previous years. This looks like northern red oak to me.
Northern red, so they would have to be over 50 years old because they're producing the acorns, right? So there couldn't have been a fire here.
Well, there certainly could have, but fire doesn't
But
kill
they
all
can-
trees.
oh,
In
so
fact,
they-
oaks are
so
very
maybe-
fire resistant
okay,
and can
okay.
absorb the impacts of fire and need fire
Okay.
to outcompete things. Like you see, in the absence of fire, you start to see maples and birches and different things like that come into
Okay.
here. The other thing I see is chestnut oak, so we see a lot of those on the floor.
He's eating it.
Hey, do we have everybody?
Yep.
I've got some money. I'll show you guys.
Excuse me, something's going back.
But what I have here, I don't know how many can see this. Geologic cross section. Okay? And what we're looking at here is the lay of the land. This peachy colored unit is the sandstone that we're on. It's called the Oriskany sandstone. It's a place name that comes from New York. Anybody here from New York? Know where Oriskany is?
Yeah.
Okay, so a lot of our geologic terms come from there. It's the wrong rock unit name, but we don't worry about that. But there's actually a formation called the Ridgely that this actually is, which is in West Virginia. But the West Virginia Geological Survey doesn't use it, strangely enough. All the other surveys around do. This Oriskany / Ridgely is dipping like this. It's almost vertical. If you can see the beds, they're like this. So it's going down really, really steep. So the rock was up here, but it's eroded away. And then it dives down and goes under this landscape. It goes way down, and I don't think you can actually see it pop up again within our field of view. So it's deeply buried. The rocks over here are much younger than this rock. Okay, so it's a real common rock throughout West Virginia. It's not the big ridge former, but it's a lot of minor ridge, like Knobley Ridge over near Kaiser is made up of this rock, a bunch of other places. Chimney Rock over near Broadway, Virginia is made up of this rock, and lots of other places it shows up. It shows up a lot of places over in this direction. No, Senecas tuscarora, which is older still and further down. Right. So at any rate, it's a nice ridge former. The shale that's over there, the limestone that's over there, they're weak. So the streams, weathering, have removed that rock. So we have a valley in the shale over here, a valley in the limestone over here, probably with some caves underneath of it. But I'm not going to try to show you where I think they might be. But there are caves over here. So anyway, I just thought I'd wheel this out right now. I'll come back to it later and talk about the mechanism of what's going on. The one last item I want to say, though, we're going to be looking at a talus slope that's made up of rock of this type that have come down the hill. It's not down there. It's actually about a quarter mile that way, and then down off the side of the mountain. So if you're really into the geology of this place up here, we don't have time to look at it today, but get a hold of me. I can connect you up on another field trip, and we can talk about what's going on up there and how come the rock is breaking apart. Well, I think this whole talus slope down below here is a big landslide, which is different than what Kevin concluded 20, 18, 15 years ago. But now we find more and more of them usually associated with huge landslides. So we'll talk more about that down there. But I just thought I'd get this out now so you get an idea of what the lay of the geology underneath of the landscape is.
Mike, can we do a quick safety check?
Please.
Ethan's ready to tell you. He educated me up here. Take it away.
You gonna do a reenactment?
No.
No. No.
Guys up on the rock, please listen here.
There we were.
Go ahead.
So I was over on actually the rock you guys are on right now, and my body just went entirely limp, and it made me fall backwards off the rock, and
That way.
Yeah.
Thank God he fell away from the river.
way. And a miracle happened. Laid there 5 seconds. Mom thought I broke my neck, and I get up crying 2 seconds later. She's like, "Thank God."
Blood, but no brain matter. So when people are here, they'll start getting, especially, I don't know, the
Kids.
yeah. Sure. And one, you catch a shoelace,
And that's all that
or any way you trip, you go that way, we're gonna just be picking up pieces. So I tell people, please leave a body's length. You may skin your knee, elbow, something, but you won't die probably. Back away from the edge. No guardrail. I haven't left anybody yet, but I would be tempted if somebody was being stupid out there saying, "Hey, I can't be part of this. You're not following directions. I'm out here."
And in case you're wondering, Steve can run down the mountain.
Yeah, he ran
he
down
can.
with carrying you.
No, I carried him.
Oh, you
That's
carried him.
A miracle.
And as far as when you're leading trips up here, the whole preserve is 149 acres, and our hike covers about 4 acres of it or so, probably. Considerably more, but we don't cover but a fraction of what the preserve is on our guided walks. A couple of reasons. One, we don't have a formal trail network through the remainder of the preserve. I've done some hikes all the way out the ridge. Steve was talking about if you want to learn more about the geology and look at the talus slope from up top looking down, you can continue out this ridge. It's a wonderful hike, but it's not a hike that's really made for most visiting public. So
Greenbrier.
Greenbrier, rocks, unimproved trails, no trail, no signs. So generally we'll stop here. If later in the year we want to get a smaller group together and go exploring, I'd be totally fine with that. But generally just your tour stops here, and then you turn around and retrace your steps.
Okay, I'm gonna do a little session, and I know I can't reach everybody, but I just want to go ahead and explain the data I have here. I go back. How did I come here? Somebody talked me into it. It wasn't Steve, but it was
Tina
Hall.
I saw Tina 2 weeks ago, by the way. She said to tell everybody hello.
Okay. I actually never met her in person. We talked on the phone, and she kept trying to get me to get a student involved over here. And it took me about 2.5 years to do so. And by that time, she was gone to Michigan to work
she's
with.
still in Michigan.
Yeah. Anyway, so I never really got to meet with her, but she gave me some great ideas of what to do here. And I wasn't really aware of the place and all that's unique botany that's associated with other plants. But I was intrigued by the issue of why here and not a million other places or thousands of other places. So we started doing a bunch of things, including geologic mapping, that led to this diagram that I had up earlier. And I'm going to pull it out one more time. Alrighty, we're up on top. We didn't get into this limestone belt on yonder side of the mountain, but we were up on top in this sandstone. And as Steve was just saying, Kevin kept trying, and my master's students kept trying to connect this limestone on this side to this side. All right, because some of the algific talus slopes in Iowa are in limestone landscapes and they're associated with caves. The Kevin was a caver. That's probably why I was able to talk him into coming out here. Alrighty. So anyway, so he spent the best part of a year trying to convince me. I pretty quickly decided that wasn't going on. He took the best part of a year to convince me that it wasn't. And in the end, he got it right. And he realized through some very difficult field work. Alrighty. So anyway, underneath of us, if we were to see the bedrock, and you can if you walk about 300 maybe feet, 400 feet upstream, you can see the bedrock. It's the shale. It doesn't have caves in it. You can't form caves in it. So the cave system just doesn't work because it's on the wrong side of the mountain. But what we do have is a lot of rock coming off the edge. And that's this talus slope that you can see. Now, one thing that Kevin found in his geophysics work is that this talus slope, unlike most of them, isn't a meager 2 to 4 meters, 6 to 12 feet, maybe 15 feet thick, like most talus slopes in the Appalachians. They're, they're thick, but, a lot of times you see this talus slope and you dig down one boulder and it's in the dirt. Alrighty? Here, it's 60 feet. And he was able to do that through a device, a trained conductivity meter, which is a device where there is an emitter and a receiver that are 10 meters apart, 32, 33 feet apart, on the end of either end of a rod. So he's walking back and forth across that slope with this 33-foot long pole and heavy instruments that go with it, doing this geophysics. And he got all kinds of people to help him do field work one day. Yeah. His dad was the only one who came back a second time.
Not a third, probably.
True love, no, true love. The one time that he had his field work interrupted because, you actually think about it, because this is cold, you're not likely to find snakes here. They'd be sluggish or whatever. Not to say that you'll never find them. When you get to the edges of the talus slope, that is not true anymore. And the day that he set off the rattlesnake twice was the day when he ended his field work a little early. So, but you don't need to go up there. I would not recommend going up there. Every rock up there is teetering. And when I do go up there, I do have some, once a year I go up and monitor some temperature loggers that I have up there. And when I do, I make sure there's always people with me, preferably somebody who could carry me out if I break an ankle. But it's often very teetery and very, very, very dangerous. But I think folks with the Nature Conservancy know you really can't study something without interacting with it. So if I didn't do things that we would not want you to let your trip members do,
yeah,
if I didn't do that, I couldn't stay.
Not only is it really tough walking because of the nature of the rocks, but the rare plant zone is basically, there may be some below the trail, but the rare plant zone is essentially from the trail to the rock. This vegetated band right here at the base of the slope where the cold air is coming out is where we have the rare and unique plants at Ice Mountain. So don't, I ask you kindly, don't go over there. Don't send your tour over there. Don't allow your tour to go over there. Don't allow a little kid on your tour to go over there that's running away from their parents. So, just kindly ask your group to stay on the trail, single file through this area, and then this is a great place that you can actually get off the trail just a little bit and get into the vents. So, I prefer that you don't get people encouraging to make new little trails up to vents off of the trail other than this one.
Yeah, this is the prime place. It's the largest of the vents. It's the one that you're more likely to see ice for a prolonged period of time. So this is the golden spot for here. There's other spots.
Hot summer day, I mean, this is it. This is where you want to be.
Yeah. I like doing field work lying right where he is.
Absolutely. We've been out here doing field work in the summer with students and things like that. This is always where we take lunch break.
Yeah, and I've been up here where I've taken pictures, infrared pictures. I was watching one of the posters I didn't reproduce. But it's 90-something up on the talus slope, and there's ice right there. So it's really cool place in many, many ways. So how does it work? Somebody asked me earlier to explain that, and this is, all right, I got it a little bit backwards here. Yeah, okay, I think I was supposed to take them out, but I'll just leave them in here. So all right, in cold weather, basically, when it gets really cold outside, then the air inside the talus is warmer than the outside air. So that outside air sinks in because it's more dense. It takes the place of the warmer air. The warmer air rises up, and you get a temperature, air temperature exchange. Okay, so cold air connects to the talus slope. Now, when it's warmer, well, cold air sinks. So it's warmer outside, that cold air loves it. It's going to hang out there. It's going to be thermally stratified because it's so dense. And the nice cover of this real thick cover of rocks means that the wind blowing by, it's not going to affect other than the top very few feet. All right, so that air is snug as a bug in a rug down at the bottom of this pile of rock, and it gradually, very, very gradually warms up. And now if this is in the fall or in the winter, it warms up a few degrees the next day, but then there's another cold air event, and another cold air event, and another cold air event. Okay, so in cold air sinks, gets into the talus slope. And then this other picture here, when it's warm air, that cold air is stratified, isolated. It's a closed system in warm temperature like today. But if we're to drop down to 20 degrees tomorrow night, it would become an open system again with cold air sinking in and warm air rising up there. Now, the cold air, like I said, it's snug as a bug in a rug. The only place it can get out are through these vents. Now, if you look at the entire area of all the openings that cold air could sink in, there's thousands of square meters where the cold air can get in. If you add up the cross-sectional area of all the vents that I've inventoried, it's less than 10 meters, it's probably less than 5 square meters. In other words, we have thousands of square feet, tens of thousands of square feet for the air to funnel in, and then not even close to 100 square feet for the air to come out. So imagine this big gravel-filled funnel, and you pour cold air in, and a tiny little spigot like a pipette clamp, letting cold air out at the bottom. And so it just comes out really, really slowly. So the effects of this cold air can last a long time. In fact, even at the end of the, well, let's say go all the way into August, the temperatures are still colder than groundwater would be around here. So that cold air is lasting, you know, a long time. And partly because there's ice that forms down there. Of course, you have to melt the ice. It takes a lot of energy to melt the ice. And so there's a physics problem there that I don't want to get into right now, but basically, it just takes a long time to melt that ice once it's formed. So I think this combination, you know, how much ice will form, how long will the ice last, is partly how cold it is in the winter and in the late spring. Another part is how much snow falls, or how much rain falls that gets converted to ice at the shoulder season. Anyway, this is a temperature data log from October 2014 to March 2015. It's just a year that I picked out. I could plot up a number of other years, but it's plotted funny. You might ask, why do I start in October? Well, I do a lot of stream studies, and October 1 is the beginning of the water year, because that's when streams are usually at their very lowest. And actually, I think, you know, if biologists were to start the year, they probably wouldn't start on January 1st. You know, there's so many things start changing around October 1st. So if you bear with me, with me going with the water years, what you see is that starting maybe the last week or two of September, but certainly by the time October rolls around, you start getting these cold air events, replacing the air, and then so the temperature, these yellow spikes here are the outdoor temperatures on a tree up there, and then the blue line represents what the temperatures in one of the vents down here. So what you see is there's a lot of ziggy-zagginess when the cold air is sinking in. As fall goes along, you get colder and colder nights. The temperature drops lower and lower and lower. It does rebound every day, but it doesn't go back to where it was before. All right, and that keeps going on all the way into January. This particular year, the coldest temperature was actually at the end of February. All right, so that system is open most of that time. And then, kind of curiously, you come here in January, which I would strongly encourage you to do. You don't see nearly as much ice than if you come here in March. Because snowfall, well, yeah, moisture comes there. It's more moisture in the air, more likely to have precipitation, and then that gets frozen by the air coming out. So the best time to really see the ice forms is March. somebody said they were here not too long ago and saw more ice 10 days ago than they did today. So, you know, but we're seeing ice. And if you look at this particular year, then we have this one long period where the temperatures outside are, you know, going up through the roof, and you have a nice warm day like today. So the outside temperatures are rising, and the temperatures where I have my data loggers and events setting right at 0 degrees Celsius, right at 32 degrees Fahrenheit, because the data logger is either in ice or surrounded by air that is being pumped over ice. So that can last. This particular year looked like it lasted up until the end of June. Okay, and then what you see, it starts warming up a little bit. I think rainfall can make a temperature difference here, but it's a very gradual, very gradual warm up. Till by the time you get to the end of September, it's usually around 10, 11 degrees Celsius, which would be about the temperature of caves around here, which would be about 52, 53, 54 degrees, and then the cycle starts over again. And that's 1 year. I have a note here on this one. I don't think I provided you with this one. In the first half of the water year, from October to the end of March, the air in the vent is colder than the air above 77% of the time for the first half of that year. 77% air in the vent colder than the outside. All right. Okay. In the next 6 months, the air in the vent is colder 99.6% of the time. So this is a different system. In the winter, it's open briefly on cold nights, extremely cold weather, and then it shuts down for a day or two, and then the next cold air comes. But a lot of times it's open. But in the summer, it's a closed system. It's virtually closed. It's not perfectly closed, but it's kind of like that. Let's see. I guess one other one I want to show here before we leave this behind. And I could do this for more years, but I plotted up 5 years going back through 2017 water year, which have been the last time I really downloaded the data. And you can see all the different years put together, just plotted on the same thing. The warmest year that I've observed here was 2012. And that one is not in this data set, but it would probably get, it would have been warmer a little bit earlier. I didn't have this data logger in for that whole year. Right? But basically what you see is the same pattern over and over again with little variations. The big variation is how long does the ice last? And it can be from 4.5 months to 7.5 months. So,
which months are those?
Starting as early as December. Well, actually, 1 year here it started in November. Alrighty, and as late as earliest January. Alrighty, that probably would have been January 2013, coming out of a real warm year. Maybe not, but then according to my temperature observations, it's lasted as late as to late June. Now, some people said they've seen ice here.
What year was that?
Late June. 2014 was the coldest one I've had here since I think the second year that we were doing this. Now historically, there are accounts of the ice lasting into September, into October, all year round.
Well, when Sharon used to come here with the Girl Scouts, they had the ice curtain.
Yeah, on 4th of July.
Yeah.
Yeah. So, and the one thing I got to be wary of, the really old accounts, because this was a dairy, so they were managing the ice. They would dig a hole, and they would put snow and ice in it, and then they cover it up, and then it would last longer. But I don't think that happened, after the 18-somethings. So the really, really early observations, I'm a little bit fuzzy on.
I don't think Sharon was alive.
No, but there
just doesn't look that
but
old.
like for instance, there is a recorded temperature that Dr. Core published as one of his books of a temperature observation here. I got it in Celsius in my mind, 3.3 degrees in August. 3.3 degrees Celsius. Right? I've never seen anything colder than 6.1. This was in the 60s. And there's another observation in the 50s that shows people will make incredible measurements that don't match anything I've had here in nearly 20 years of measurement. So what it's actually arguing is that we're getting a signature of climate change over a pretty short period of time.
How many years does that take? What's the math on that? How many years? What's the biggest difference in?
Well, I've been studying this since 2002. Okay. 2003 is the first full year I've had data. Okay. So I've got like 16 years of data. Okay. And again, those people in their spot out measurements are seeing things that I'm just not seeing in 16 years.
Question.
And at Beartown, there's an ice cream chronology. The superintendent there, Mike Smith, used to collect ice cream on the 4th of July every year for he and his kids to make ice cream with. And he did it year in, year out, his first 13 years at Beartown. And in 1998, he shows up to make ice cream. There's no ice cream. There's no ice.
1998?
Yeah, all right. After that time, it's been an every other year proposition. So something I think has actually happened in my lifetime to these cold air traps. It's not just Ice Mountain, Beartown, it's pervasive to most of these cold air traps. They have a history of ice lasting a lot longer than they do now.
So my question. You'd say mostly it hit in the last 20 years. The biggest changes happened in the last 20 years.
I wish I had enough data.
Hard to say, right?
Yeah,
I mean,
wish I had
you've been
enough
collecting
data.
during that
The thing
time.
is, people will come here. Here's the problem I see with, because you can go back and you find all these publications that say the same thing. You know, that, you know, so-and-so reported the ice last year. They don't tell you what year, and they don't tell you, you know, what day or what the temperature was. So everybody's kind of reproducing the same story.
Okay, so
ice lasts here until September, and it's 38 degrees year round. Well, the other thing is 38 degrees year round, which I think I might have heard from the people who are doing the pros here. And then we put the data loggers out. It turns out the average temperature is right around 36, 38 degrees. The average temperature. But it's not 38 year round because it gets really cold. But it gets into the low 50s.
So you've got anecdotal evidence.
Yeah. And what I'm loving to find would be like the journals where so-and-so were here and they took a thermometer on that date and make an observation like that. And then I can actually plug it in and compare it to what I've got.
Dorothy, what do you have? Well, I just had a question. Okay, so you're just measuring the temperature here at the vents. There's still ice under the mountain the whole time.
Yeah, and
you don't know how big
we
the ice
talked
is.
about tobacco.
Oh no, you don't want to get into the mountain.
No, yeah, you're right. But what happens is, the temperature around the time that it leaves zero starts fluctuating, right? Because in the time when there's ice around it, the temperature changes like 1/10 of a degree, 2/10 of a degree a day, right? And then a couple days later, after it rises up about 1 degree Celsius, well, you'll see it'll change 3 degrees in 12 hours.
Because there's not as much
Because
ice there to keep it cold.
There's not as much ice, yeah. So
plus, in the summer, you've got warm rain coming in. You've got the air warmer. Everything affects the temperature of the vent.
But still, there's a capacity there because there's so much. Again, there might be ice really deeply pretty late in the year, but I don't think it lasts year round because the temperatures do come out to be around what you'd find in caves by the September. So I don't think the ice lasts year round. And again, I don't think the locals were digging 60 feet down to find the ice as well.
Here's my second question. Why did the vents come out here? Why didn't they come out closer to the river or at the river level?
I think it's this big landslide has come down. The river's buffered the edge up, and if you think about it, where would be the best place to have that safety valve? If the river wasn't here, we might not have these vents, because they might, or if the river were way over there, the vents might be filled with silt and sediment. So I think the river coming in, cutting the toe of the slope, is part of, this slope comes down, feathers out, and it does that. And the vents are where it does that. So I think that the fact that the river's come up against here is part of why this is a special place. Yeah, and also the other thing that happens, if you come here in March, sometimes it's plugged up to where the opening's that big, with the air streaming out 2 miles an hour.
It's like that about 10 days ago.
Yeah. Yeah.
It was just,
up with ice?
It was plugged with ice except along the bottom.
Mm-hmm. And the icicles do that. Because the water's dripping out and the wind is blowing them out, so they're growing, bucktooth, so to speak. Alrighty, but what happens when that happens is that new vents start crawling up the mountainside. So you'll see, the temperatures here will, get cold earlier, but then I've got some pseudo vents further up the slope, and they'll start getting colder later. Because basically the whole system is just filling up with air. It's got to find another vent.